Our next presenter is Michael, there we go, from the other way. Michael from Spectral Compute.
So I'm Michael Søndergaard. I'm the CEO and co-founder of Spectral Compute. And for a while, we've been working on this thing that I'm incredibly excited to talk about today. So beyond CUDA, we're here because CUDA is awesome, right? CUDA is, in fact, so awesome that NVIDIA have practically a monopoly in the GPU market by a wide margin. And now they do that because CUDA is the de facto standard for GPU programming. There's a massive, massive ecosystem of CUDA libraries out there maintained to this day, and it's thousands upon thousands of applications and libraries. It's not the only thing. There are many other attempts allowing developers to do GPU programming. What they all have in common is that they're not CUDA. So developers are stuck deciding between the difficult choice of just only running on one vendor, in which case it's often NVIDIA because they do have the majority market share, or maintain multiple versions of their code base. I'm not just talking about kernels, I'm talking everything surrounding the toolkit, all the plumbing, everything. So while all these options are really cool new languages, and that can be exciting in itself, and it's cool to hear about new things, what you don't get with this is the world that we pose in. So imagine the possibility of just staying within the CUDA ecosystem, get access to all of these thousands and thousands of libraries on all of the vendors. In fact, the best vendor in town at the moment is AMD. So that's what we're doing with Scale. We're compiling a superset of CUDA to AMD. No emulation, so there's no intrinsic overhead, because a lot of the CUDA language in PTX has straight up analogs for AMD hardware. There are some differences, but we believe we can deal with them in the compiler and the runtime. So the world we want is one just like we've got for CPU programming, where you write your code once and you just recompile it when you want to target different hardware. We have to, in order to do that, we have to be fully compatible with NVIDIA's variant of C++ and CUDA. Now, it's not perfect. It's got some quirks. Here's one of them. But if we didn't do this, there's a whole bunch of legacy software out there that won't compile. And so we could be strict and say, oh no, this C++, that isn't what we like. But we have to be pragmatic in order for this to work. So we one-to-one support the semantics of NVCC and its flavor of C++ specifically. We're at about 90% support for the core CUDA math APIs. It's just talking about core CUDA. There's more to it. When it comes to the CUDA runtime and driver APIs, around about 70% is currently today supported by a Scale in our unstable versions. Now, aside from this, there's a bunch of extras to CUDA, all the CUDA-X libraries. We could get into that, but it's not included for here. When compiling CUDA for other architectures, a major thing we have to consider is that it was designed only for NVIDIA hardware. Now, that doesn't mean NVIDIA's hardware is best for everything. In fact, AMD's best GPUs at the moment, the MI300X plus CDNA cards, they all have a warp size of 64. And so there's a lot of CUDA code out there written in a way that it makes assumptions about the warp size. But as it turns out, if we just emulate 2 warp 32 warps with a single 𝗏64 AMD execution model, most code works just fine. In fact, just a few cases where you've got some control flow that turns bad, it's a bad idea. But other than that, it'll work just fine. So with Scaling Addition, in order to allow developers to natively exploit the 𝗏64 size on AMD, we implement compiler warnings to make their life more easy. And it works for inline PTX, which we'll get into now. That's another major problem, right? Because a lot of CUDA code out there has inline assembly in the form of PTX. Now, it's not actually true that this PTX is inherently NVIDIA optimized, because in this case, what we're doing with 𝗏𝗏 is emitting some direct machine instructions that execute faster on AMD than they do on NVIDIA's own implementation in hardware of 𝗏𝗏. We do some pretty cool brute force stuff in order to produce this. It's just an example. There are more of these. So for all of its qualities and how great CUDA is, there's some improvements that can be made. And I'm not going to get into all the grits, but essentially, we're building these out and maintaining backward compatibility across all the platforms we support. And by the time that we add NVIDIA support into our compiler as well, you will be able to benefit from these features on NVIDIA's platforms in addition. I'm really excited to share this with you today. It's hot off the press. Nobody else has seen it. We thought this was the right forum. So the Virginia benchmark suite is written by researchers at Virginia Tech a while ago. We've executed them in a virtual environment on the AMD MI300X on runpod.io. And in general, things are looking quite a bit promising when comparing to baseline over HIP. On average here, we're about 2 times faster compared to HIP. And in the case that we're slower, it's typically a thing we know how to improve over time. So for the time being, we've actually only focused on compatibility with scale. Performance hasn't really been our focus yet. So when we get around to focusing on performance later this year, when we've increased our core compatibility KPIs, I'm pretty confident we can make some of those red bars be blue. So to recap, what we're doing is doubling the amount, at least, of GPUs that you can target and run from CUDA. You can stay in the same CUDA ecosystem as you'd like, or as you've always been used to. We're doing so with up to 2x performance benefits over porting efforts with HIP. And in addition, as you all know, AMD hardware is generally more affordable. So it's even easier to get started with HPC and AI compute. If you scan this QR code, that takes you to our Discord. Please, everyone, what I'd like you to do is join the Discord, reach out to us, send us hate mail if you try the toolkit and it isn't working for you. And let's collaborate, because those CUDA-X libraries are a grunt of the work. We'd love to work with all you guys on open source re-implementations, extensions of the ROCm ecosystem to just target all the hardware. All right, I think Jeff's signaling me. So thanks, everyone.
Awesome. Thank you so much, Michael.